So, welcome again. So, in the last set of lectures, we have been talking about the Sommerfeld theory, and we also derived the what is called the Fermi energy or the Fermi sphere from it, from what Sommerfeld used. So, Sommerfeld theory is basically an interpretation or the basic use of the quantum theory, where we saw that the imposition of the periodic boundary condition. Uh, Made the wave vector quantized. So not every value of the wave vector kx, ky, kz is possible, but only some quantized values are allowed. So we also derive the Fermi velocity, Fermi momentum from it. Now, in this lecture, we are going to learn about the density of states. So recalling some bit of our counting statistics, let me write the heading. Density of states calculation. Let us just recall what we learned. What was our counting statistics? N was twice, this is for the spin degeneracy for up and down spins, summation over all the k states. For me Dirac, epsilon k minus mu. Alright. And in the continuum limit, this gets transformed into 2 times v over 2 pi cubed times d cubed k times the Fermi Dirac distribution. I'm writing chemical potential because in general you have a non-zero temperature. Alright, so mu at T equals 0 Kelvin is given by the Fermi energy. Alright, so replacing this, so now we want work. We want to work at T equals 0 Kelvin. So N is 2 times V over 2 pi whole cubed D cubed K times Fermi Dirac distribution epsilon K minus epsilon F, which is the Fermi energy. Now, from this, we are now going to do a manipulation. So taking V out of it, so taking V and just pushing this twice D cubed K by whole cube times the Fermi Dirac distribution. All right. So there's a specific reason why I'm doing this. So this is a separate term altogether. Now we want to denote it by B. So N is B times, we want to denote it by GK times BK times the Fermi Dirac distribution. All right. So I'm going to explain this to you why I'm using this GK dk in place of 2d cubed k by 2 pi whole cube. So I'm going to give you an interpretation why am I doing this. It's going to get clear as we proceed down the derivation. So our GK dk is now 2d cubed k times 2 pi whole cube. All right. So now, if you recall our last lecture where we talked about the Fermi sphere. So this was our K space. This was our K space. So this was Ky, this was Kx, and this was Kz. And the momenta states were distributed like this. all around they were distributed. I'm writing, drawing just a few to explain it. Now, we told that there's a certain boundary up to which the energy levels are filled with up and down electronic states. All right, so up to a certain, so all right, so up to a certain distance, which is kf for me wave vector, we have a sphere which encloses all the energy levels that are filled with electrons, spin up, and spin down. So the Fermi sphere contains all the electronic states that are filled. All right. So now the beyond this Fermi sphere, there are levels present, but it's not filled with the electrons, but rather they are vacant. So now in K space, as we did used to do in real space, that we are taking a sphere and we are taking a shell outside it. So it was a differential volume. So in this case also, if this reminds you, is d cubed k is actually 4 pi k squared dk. If this is the Fermi sphere and I draw a thin shell around it, if this is your Fermi sphere, this is your, sorry, this, yeah, write it like this. If this is your Fermi sphere, now you want to draw a thin shell around it. Thin shell around this Fermi sphere, inside of which are the electrons present. All right. So if the Fermi sphere has a radius k, and this is dk, and if this is dk, and if this is dk, then the volume of this spherical shell is given by 4 pi k square dk, or d cubed k, volume of the spherical shell. Understood? So volume of this shell is 4 pi k squared dk. Now it is around this Fermi sphere. So you are considering a thin spherical volume outside this Fermi sphere. So now you are slowly realizing that why am I using this d cubed k? So this is the volume of the spherical shell around the Fermi sphere. All right. So let me just see. Let's record. Yeah, let's record. So for this spherical shell, there's no theta or phi dependence. Only it depends on the radial length. All right. So it depends on k, the vector, and which is the radius of the Fermi sphere. It need not be a Fermi sphere, but just consider a spherical shell that contains some electronic density of states, and those are filled. All right. So now, if this is your differential volume, so till k, if you do an integration of this, you'll get what is 0 to k. Break this down, 4 pi k square dk. This is the volume of the sphere in k space. So integrating this differential volume, you will get the volume of the sphere. So now the volume of the shell is 4 pi k squared dk. So we are working in the k space only. So that the k, the d cubed k volume in k space will contain electronic states, natural electronic states. Now the question is how many states are there? So in a volume, so the question we ask, in a volume d cubed K, how many electronic states are present? States are present. This is the question we ask. But there's a reminder that the momenta states are discrete. Momenta states are discrete. All right. Momenta K states are discrete. So number of electrons or states, number of electronic states between K and K plus dk. If you notice the diagram, I have drawn a sphere with a radius K and I have drawn a spherical shell around it with a thickness of dk. So the outer sphere has a radius K plus dk and the inner sphere has a radius of K. So the spherical shell is the volume between the sphere with radius K plus dk and the sphere with radius K. So that is the definition of a spherical shell. So number of electronic states between K and K plus dk. So number of electronic states in the volume d cubed K. So I've already calculated the volume d cubed K, which is 4 pi K squared dk. And we also have to remember that there will be 2 electrons in one momenta state because there will be up and down spins. So it will be multiplied by 2 times the volume of that spherical shell, which is 4 pi K squared dk, divided by the smallest volume in the K space, because you know that not all the space is allowed for wave vectors, only the smallest volume containing a single momenta state, which is K, and which is a summation of Kx, Ky, and Kz in the respective 3 directions. So the smallest volume available is 2 pi by L cubed. This will automatically give you, if you think about it, this will give you the number of electrons or electronic states in this volume d cubed K. All right, so your L cube is V, L cube is V. So you can easily write as twice times V times 4 pi K squared dk by 2 pi cubed. So you can just simply write that number of electronic states between K and K plus dk per unit volume. Per unit volume V is twice 4 pi K squared dk over 2 pi cubed. 2 pi cubed. Fine. So this is density of states. Density of states times dk, because in that dk radius, how much is the density of states? So this will be the proper definition of what we have been calculating. The number of electronic states within K and K plus dk per unit volume is this, which again can be interpreted as the density of states times the thickness of that spherical shell, which is dk. So this is again twice 4 pi K squared dk over 2 pi whole cubed. And now you relate that we are going to write this as g of k dk. We name it as g of k. The density of states, we name it as d of k, g of k. So this is 4 pi K squared dk over 2 pi whole cubed. Now, if we go back to the earlier derivation, what we saw is that we wrote gk dk is twice times d cube k over 2 pi whole cube. Now you can understand why I've been telling you this, that this is the interpretation of the density of states. We didn't write out of the blue that 2 times this is also can be written as 2 d cube k over 2 pi whole cube. So it's not out of the blue that we wrote gk dk. This is density of states times the thickness of those of that spherical shell. So gk is your density of states. So now you have the physical interpretation of writing that gk dk. So density of states, of course, per unit volume. All right, per unit volume v. So now, going back to what we wrote earlier, we wrote it as n is equal to twice v. Sorry, this is we wrote it as twice d cubed k over 2 pi whole cubed times Fermi Dirac epsilon k minus epsilon f, which is again can be written as n over v, which is which is the number density of electrons in the sample. All right, so which is given by twice d cubed k by 2 pi whole cubed times the Fermi Dirac distribution. Now, a few moments earlier we wrote it as gk, the density of time states times dk times the Fermi Dirac distribution. All right, now we clearly understand why we wrote gk dk. So now this is the density of electronic density of states. So this is n is gk dk times the Fermi Dirac distribution. Fine. So the density of states is gk dk. But remember that we wrote ek as h cut squared k squared over 2m. It doesn't matter which space you are working in. It doesn't matter if you write k or if you write in terms of g of ek, because both are interchangeable. So whether you want to work in wave vector or you want to work with the energy itself, it doesn't matter as long as the number n, the number which is the number of electrons in the sample, is constant. All right, doesn't matter what you work with. So the energy levels were like this. You have the continuous distribution of the energy levels. You can denote it with the wave vector. Of course, you can denote it with the wave vector k1. This is k2. This is k3. This is k4, k5, k6, and so on. On the other hand, you can also write it as ek, sorry, e1. You can write it as e1. This is e2. This is e3. This is e4. This is e5. This is e6, and so on and so forth. So it doesn't matter what you are working with. So if this is so, this implies that g of ek is g of k times dk d of ek, which can be written as gk dek dk of inverse of it. All right. So your gek dk is number of states between ek and ek plus dek per unit volume. Just like we wrote GK DK. Sorry, this is my mistake. This should be your D of EK. Just like we wrote GK DK, we wrote somewhere GK DK density of states. GK as density of states per unit volume, and GK DK number of electronic states between K and K plus DK per unit volume. Similarly, we wrote GEK D of EK as the number of states between the energy level EK and the energy level EK plus D of EK, and which is divided by the volume. So we have two definitions in terms of the energy or the wave vector. But these two define the same thing, which is N, which is also given by GK DK times the Fermi Dirac. All right. It is also given by G of EK D of EK times the Fermi Dirac distribution. All right. Let me remind you, GK was 2 into 4 pi k squared by 2 pi whole cubed. Epsilon k was h cut squared k squared over 2m. So formally, I should write the definition of G of EK also, which is density of states at energy EK, which is given by number of states per unit volume, per unit interval, per unit interval of energy. Let me remind you of the sphere, the spherical shell, number of states per unit interval of energy DEK per unit volume at energy EK. All right. So now we can write G of K. So G of K is 2 times 4 pi k squared dk. So this is 4 pi k squared. This is 4 pi k squared over 2 pi whole cubed. So and EK is h cut squared k squared over 2l, which implies DEK times DK is h cut squared k over m. So if you have to write G of EK, which I already told you is G of K, no matter what you work with, D of EK, D of K, now let's put the values here. 2 times 4 pi k squared by 2 pi whole cubed, right? Times your D of EK is 1 by h cut squared k by m. Now you wrote G of EK, means you want the density of states as a function of the energy. So use the interconversion between EK and K. So you can write 2 into 4 pi by 2 pi whole cubed times K squared is 2m EK by h squared. And also this is h cut squared over m, we got the 2m EK, which is k by h cut squared. So this is simply putting the values of k. All right. So now this is simplified as 1 by pi squared. We have 2m EK by h squared from here and m by h squared from here and 1 by root under 2m EK by h cut squared. So these two terms will cancel out between themselves and produce only a square root term, which is root under 2m EK by h squared times m by h squared. All right. Now this can be slightly manipulated to write as 1 by 2 pi squared 2m to the power 3 over 2 by h squared cubed times ek raised to half. Simple. This is just a simple manipulation, and there's a reason I'm writing it discretely like this, because in earlier lectures, you know the definition from earlier lectures, you know the definition of the Fermi energy, which is h squared over 2m times 3 pi squared n raised to 2 by 3, which implies EF raised to 3 by 2 is h cubed over 2m raised to 3 by 2 times 3 pi squared n. Now, in the earlier formula for G of Ek, you had 2m raised to 3 by 2 by h squared cube. So now you can use this EF formula in there also. So your G of Ek is 1 over 2 pi squared, which is your which is 3 pi squared n over EF raised to 3 by 2 times Ek raised to half, which is again given by 3 by 2 n by EF times Ek by EF raised to half. So you are getting the density of states in terms of the number density of the electrons and the Fermi energy. Of course, it contains also the energy Ek at which you are calculating the density of states. So Ek by EF raised to half. All right. So I told you earlier that no matter what, you can work with either the energy or the wave vector itself. So what we did is we transform from the K wave vector to the energy. All right, we wrote the formula from the definition of the Ek, which is h squared k squared over 2m. That is your energy that you get from solving the free particle wave function using in the Schrodinger equation. So this is now what we have. So one thing to notice is that your density of states Ek is proportional to Ek raised to half. So if you have to draw the graph, which is your this is your graph. So the curve will be parabolic. So this is your e raised to half. This is your energy axis, and this is your density of states. Now, if you have to calculate the density of states at the Fermi energy, you just put EF in place of Ek. So G of EF comes out to be 3 by 2 n over EF, just from this equation itself. So 3 by 2 n by EF. All right. So the density of states at the Fermi energy is a function of the electronic density of states, electronic number density divided by the Fermi energy. So in earlier lectures, you saw for copper, N is 8.45 into 10 raised to 22 electrons per cc. And EF, just we learned it in the earlier lecture, in the last lecture, which is 7 electron volt. So if you have to calculate the density of states for copper at the Fermi energy, this will be given by 8.45 into 10 raised to 22 per 7 electron volt. So roughly you have, this is 8, let's consider it 9 to the 27 and 14 to the 28, which is roughly of the order of 10 raised to 22 electrons per electron volt. And if you remember, we said that GEF or GK is the density of states, which is the number of electrons per unit energy. So this is N over dE. All right. So this is what you get. So fantastic. So now the N, which is combination of G of Ek times the Fermi-Dirac Ek, E of F times D of Ek, which is also given by B G of G of K times the Fermi-Dirac times Ek minus Ef times D of K. So now, what does this term G of Ek times the Fermi-Dirac distribution mean? This is what you call the density of occupied states, because GEK gives you the density of states and you multiply it with the probability distribution. Basically, the Fermi-Dirac distribution is the probability of occupancy. So you have a density of the states, a distribution of the energy states, and then you multiply it with the probability, which is the Fermi-Dirac distribution. So it will give you the density of occupied states. Density Fermi-Dirac distribution will give you the occupancy of the electrons in those energy levels. So naturally, this product will give you the density of occupied states. So redrawing the graph once again. This is your G of Ek. All right, e raised to half. This is your G of Ek. Fine. Now, if you do the product and your Fermi-Dirac distribution at t equals 0K is like this. So this is your Fermi-Dirac distribution. So this is 1. So now, if you do a product of these two graphs, what you get is the density of occupied states. Density of occupied states. This is G of Ek, which you multiply it with the, so G of Ek times the Fermi-Dirac distribution, and this is at t equals 0. This is at t equals 0 Kelvin, and this will give you the density of occupied electronic states. This is your density of occupied electronic states. Fine. So now this is the calculation at t equals 0 Kelvin. But now if you have to do it at a finite temperature, if you recall, our density of states did not in anywhere require the effect of temperature, because in the quantum model you do not, the electronic behavior does not behave as if it depends on the temperature, which it did in case of the Maxwell-Boltzmann distribution. With increasing of temperature, the distribution of the electrons spread. So there is no temperature involved in the density of states. But at finite temperature, your Fermi-Dirac distribution will be like this. So this was your E F or mu. Sorry, this should not, I should not write it as EF, because in that case you will think that it is at T equals 0 Kelvin, but this is mu, and this is your Fermi-Dirac distribution. This is 1 and this is your E. All right. So now if you do a product of these two terms, what you get is the density of occupied states will be like this. Density of occupied states will be like this. So it goes parabolically. Now it shifts, and because it is multiplied with a fraction, so in this it will be with energy. All these graphs are with energy. All right. So for finite temperature, G of EKFD will be like this, and this will give you the density of your occupied states. Occupied. This is vacant. All right. So this is what you get, the multiplication of FD and G of EK. In the product of these two terms, you get the density of occupied states. So in this lecture, we learned about how the electronic density of states formulate to. So it is that the in three dimensions, the density of states is proportional to e raised to half. And the Fermi energy, the density of states at the Fermi energy is dependent on the number density of the electrons and the Fermi energy itself. So for copper we calculated it is very, very high. And also we looked at how the density of occupied states look like. So this is the summarization of the lecture. Now we want to end here the Sommerfeld model. Probably in the next lecture, we will make a brief summary of the Sommerfeld model, what we learned out, because from starting from the simplest roots approach, which was a very fantastic theory, we transitioned into this Sommerfeld model, which is a quantum theory. Alright, so we learned too many of things, so maybe it's better if we do a recap of what we learned about, a brief recap of what we learned about in the next lecture. So let us just stop here.